Okay. So simplifying square roots. Now this is something I believe you should have covered in your algebra class last year. Okay, that's my understanding at least. My other geometry class said that they had covered it. Now they didn't really remember it that well, but they still did cover it. They kind of was, you know, familiar to them. Okay. So the basic thing is something like this. All right, if we have, for example, the square root, like, how do you simplify something like the square root of 50? Okay, that's kind of our question. Okay, so if we were to try and just like type it into our calculator right now, and just say like, calculator, what is the square root of 50? And you hit enter, this is what you get, a decimal. Okay, and it's a special kind of decimal too, because this decimal, will it ever repeat? No. And does it ever end? Yeah, no, it does not. Okay, and you might get to a point where it's like, it looks like it repeats, but if you go far enough, you'll find out that it really does not end up repeating. This never, like, repeats itself, you know, regularly. Like, you know, 1/3 is 0.333333, so that, you know, is repeating itself. This never gets to that point. It's always going to be like this, okay? Does anyone remember what do you call, what set of numbers does this fall in because it's got a non-repeating, non-terminating decimal like that? Anyone know? So it's called irrational. These are the irrational numbers. They're irrational. Okay, rational numbers can be written as like fractions. Okay, so like 1/3, right? That's an irrational number. That's a rational number. Sorry, it's got a repeating decimal. Even though the decimal does not end, it repeats. This is irrational. This cannot be written as rewritten as a fraction, and it has a decimal that goes on forever and never repeats. Okay, so it's an irrational number. So like, how do we simplify it? So we could say that square root of 50 is equal to like 7.071, right? But is that exact though? Yeah, no, it's not, right? So saying square root of 50 equals 7.071, that's technically not right. So in math, if you want to show like it's like approximately 7.071, you can put a squiggly equal sign like that. Okay, so a squiggly equal sign. So we should say it's approximately 7.071. And sometimes that's what you'll be asked for. You'll be asked to just like give the square root of 50 as like a decimal. Okay, so you can like sometimes you can just like type in your calculator, get an answer, and like just round it. Okay, that's fine. But again, it's like, is that the best we can do? And the answer is no. There's more we can do with this. Okay, and so what we want to look for here, right? It's like, well, we know how to simplify. What about like, how do we simplify the square root of 25? It's 5. Okay, so. It's square root of 25 is 5, and so like, Hunter, how did you know that the square root of 25 was 5? Right, okay, so 5 squared equals 25, right? So if we take the square root of both sides here, all right, we end up with just that 5 is equal to the square root of 25 then, if we don't simplify the right-hand side. So the square root of something squared becomes just 5, so square root of 5 squared is 5. Square root of 25, you know, I could take that square root still, but we can leave it like this too. 5 is the square root of 25, okay? They are the same thing. So that's easy. 5 is a perfect square. Is 50 a perfect square? Yeah, no, it's not, right? But 50 we could rewrite as a product, right? 50, and it's a product of 25 and something else. So it's 25 times what? Anybody? 2, that's right. So we go back to our original question here. If we say that the square root of 50, okay, that's going to be equal to the square root of 25 times 2, like that, right? Isn't that the same thing? Okay, didn't do anything crazy there, just rewrote the 50 as 25 times 2. But now, why do we bother doing that? Well, because, as Hunter pointed out, 25 is a perfect square. So that means I can break this up. When you have a product underneath the square root like this, okay, that's equal to the product of the individual pieces, the square root of the individual pieces, like that. So square root of 50 times, or is equal to the square root of 25 times 2, which is equal to the square root of 25 times the square root of 2. And so, like Hunter said, and like some of you guys, well, not just Hunter, I know other people said it too, but the square root of 25 we know is 5. So we can actually simplify this piece, and it becomes just 5. And then that square root of 2, can that be simplified any further? Yeah, 2, we can't even break 2 down anymore. 2 is prime, and so it won't divide up anymore, and so that's how we know we're done here. And that is the simplified version, okay, of the square root of 50. All right, is that familiar to you guys? Is that like ringing a bell? Yes? Okay, it's ringing a bell? Good. Okay. So, now, did you guys do it this way, or did you guys do like the factor tree? You did the factor tree? Okay, do you guys prefer the factor tree then? Yeah. All right, so you want me to show you the factor tree then real quick? All right, so factor tree is if you take the square root of 50, so like this is, or, if you take the square root of 50, and you just kind of like break down the number 50. So it's like you just pick any number that divides 50. So like 5 and 10, for example. Okay, 5 times 10 gives us 50. Can 5 break down any further? Yeah, no, so we're done there, but can 10 break down any further? Yeah, and that's like 2 and 5, right? Can 2 break down any further? No. Can 5 break down any further? No, they're all prime. And then once you have the factor tree written, what did you guys do? Yeah.
If any numbers are like, if any numbers are similar, like you to the numbers?
Yeah, if you have any pairs, you're looking for pairs. So I see I have a pair of 5s here, okay, just like that. So that pair of 5s, okay, that means I've got 5 squared underneath the square root. So if I can pull those out front and just call that a 5, okay. But what didn't get paired up? The 2. So the 2 stays underneath like that. And that's another way to do it too, okay. So either way that's kind of like comfortable for you is fine. And we'll do some more too, so don't think that's like it. Okay, it's like, all right, now you got it, now we're moving on. No, so we can do a few more here too, just for some practice. All right, so let's see here. How about like, okay, let's try that one. What about like simplify, let's say the square root of 48. Okay. And again, we'll do it both ways. So let's do it the factor tree method first here. So let's see here. So what can divide this evenly here, Julie? What can we divide 48 into?
24 and 2.
Yep, sure, 24 and 2, that works. Okay. Can 2 be broken down any further, Julie? Can 24?
12 and 2.
Sure, 12 and 2. Okay, I'm seeing a pattern here. Very good. 2 can't be broken down any further, but what about 12 there, Julie? 6 and 2. Okay. And then 6 can be broken down into? 3 and 2. Lots of 2s there, okay. All right, so let's see here. So Maria, do you see any pairs here then? All the 2s are pairs? So we have, well, let's see, you've got one pair of 2s right there, right? And then another pair of 2s. So each one of these pairs, we're going to pull those outside the square root, right? This is like saying 2 squared. And if you take the square root of 2 squared, you're left with just a 2. So that pair becomes a single 2 out front. And then this pair also becomes a single 2 out front. And then, Maria, what's left inside? What didn't we pair up? Okay, so those are there, but we only want to use the numbers that are like that are prime, the prime numbers there. Like we don't need to worry about any of those guys. So really, what's the only other number left? 24 we broke down further, 12 we broke down further, 6 we broke down further, but the 3 we did not. Yeah, so the 3 is what's left over. And so that becomes then 4 times the square root of 3. Okay? So yeah, 4 times the square root of 3 is there. Okay, so that's your final answer right there. Okay, alternative to that, right, we could have done the thing that I was kind of trying to show you there. Again, 48 is just a matter of like, okay, square root of 48. Let's see here. You want to look for perfect squares that divide 48. So I always like to try 4 first. So 48 is equal to 4 times 12. And so it's like, okay, so that's equal to the square root of 4 times the square root of 12. Square root of 4 is 2. Right? But 12, though, that's also divisible by 4. So I can do like 2 times the square root of 4 times 3. Oops, sorry, I'm off the screen now. And then I can break that up again. 2 times the square root of 4 times the square root of 3. And so the square root of 4 is 2, so I get 2 times the square root of 3, which is then 4 times the square root of 3. Okay? That's another way to do it, too. It's up to you which one you like there. Both kind of work, as long as you get it down and stuff like that. All right? Anyone want to see another one, or are you guys ready to try one on your own? You're good? No one needs to see another one? We're all good? We're all good? Okay, so here you guys try. So I'm going to give you 2 here to try. So try, let's see here. So let's have you try simplify the square root of 63, square root, let's see here. The square root of 42. So 1, 2, and then also one more here I'm going to give you. Square root of 192. Okay, so try those 3 there. Give those a shot real quick. And you may use calculators if you wish to help you. You can multiply those out too if you want to get it. So where's your okay, gosh. Simplify as much as you can. Yeah. All right, 30 more seconds here, and then we'll go over this. Well, hello. Thank you, Mary. Welcome back. All right, so let's go over this here real quick. So Elizabeth, the square root of 63, what'd you say that was? 3 times the square root of 7. Okay, everyone okay with that? We're good? Okay, very good. Thank you, Elizabeth. Sounds good to me. 17, not 17, oh gosh. Zishan, square root of 42, simplifies to?
I was stuck on that one.
Stuck, why not? Or why were you stuck?
Because I didn't get a common factor.
Oh, okay, so like you were able to break it down though? Alright, so what'd you break it down into?
7 and 6.
7 and 6, okay, that sounds good to me. 7 times 6 is 42. 7 can't break down any further. What about the 6 though?
3 and 2.
Yeah. Okay, and so what was the problem here?
I didn't get any more 2s or 3s.
No pairs, right? So then what is the square root of 42 if we simplify it?
I didn't get calculated.
It's okay, square root of 42.
Oh.
That's it. Can't simplify any further, that's it. Okay, that's as far as it goes. Sometimes they don't simplify. Alright, so good job there, Zishan. Alright. And then last one, let's go to Julia. What do you say for this one, Julia?
I got 3 times the square root of 2 times 2 times the square root of 2. Can I just put that as 5 times the square root of 2?
So you got this is what you're saying.
Yeah.
Okay, so we're multiplying here. So let me see here. So you would say 3 times 2, so it wouldn't be 5, it would be 6 then, right? And then square root of 2 times square root of 2, that actually would end up being square root of 2 squared. So is that? Let's see here. How do you break it down? I don't think this is quite a perfect square, but how do you break it down? What'd you say?
12 times 16.
Okay, 192 is 12 times 16. Okay, gotcha. All right.
Instead of 12, I did 6 times 2.
Okay.
And then for the 6, 2 times 2.
Oh, 2 times 3.
Yeah.
Okay.
And then for the 16, 8 times 2.
8 times 2. Okay.
And for the 8, 4 times 2.
4 times 2. 2 times 2. Yeah. Okay, gotcha. And so let's look at all these pairs we have, right? So I got a pair of 2's right there. Got a pair of 2's right there. Any other pairs? Julia?
On like the other side, there's like the 2, 2.
Aha, aha. So that still counts because it's all part of the 192. So we'll still count that together. Any other pairs? No, that's right. So we have how many pairs of 2's here, Julia? 5 pairs? I see 1, 2, 3 pairs. 3 pairs. So like I count 2 as, 1 pair is like there's 2 of them, but I count it as 1, so that's a pair, right? So 1, 2, 3 pairs of 2, so it's 2 times 2 times 2. And is there anything left over that didn't get paired up there, Julia?
3.
The 3. So just that stays in the square root. Just like that. And so 2 times 2 times 2, 8. Square root of 3. Okay? You're okay with that? All right. If not, that's okay. We'll have some more practice here as we go too. All right, so there's that. Now, why? Why do we bother with this? Why are we learning this? Why are we getting prepared for this? Because our goal now, right, is we should be able to, we're going to talk about right triangles. This whole unit is going to be talking about right triangles. And so let's kind of like refresh our memory about the right triangle's anatomy. Right? Just like you have anatomy, right? Talk about your legs, talk about your arms, your fingers, your hair, all that good stuff. We're going to talk about the parts of a right triangle. So we draw a little right triangle right here. And we'll call that right triangle ABC. Bless you. All right. Let's see here. So again, what's the name that we use for like side AC or side CB here? What do we call those things? Anybody? They're the legs. We call these the legs. So that's a leg, that's a leg. And then this third side, opposite the right angle, we always call that the hypotenuse. And it's always the more fun one to spell. So it's Hypotenuse. So right, so remember the hypotenuse, right, is always the longest side. Ugh. Let's see here. The measure of angle A plus the measure of angle B plus the measure of angle C. What's that going to equal? 180 degrees. That's right, because it's all three angles in a triangle, right? We know that all the angles in a triangle are up to 180. What about the measure of angle A plus the measure of angle B? What does that have to equal? 90? Okay, how do you know?
So you guys, angle C is 90 degrees, so 90 minus 180 is 90.
So the leftovers, A and B together, also have to add up to 90 degrees. They need to be complementary. Right? If two angles add up to 90 degrees, and they're called complementary. Not the same thing as complimenting them, like, ooh, you're a nice looking angle today. That's P-L-I-M-E-N. Okay? Complementary means they kind of like go together. They complement each other. They add up to 90 degrees. All right. So, let's see here. So, for example, we also want to be able to, so things we'll run into here, we need to be able to solve equations, with squares and square roots. Okay, we need to solve equations with squares and square roots. So, for example, am I going too fast, by the way? We're all good? Okay. Solving equations with squares and square roots. So, for example, here, we should be able to solve something like this equation. Oh, well, whatever, okay. 13 squared equals x squared plus 5 squared. We should be able to solve an equation like that. Right? So to solve this, let's see here. So Michael, to solve this equation, how might we go about solving this equation here for x?
First you have to square it. So 12 squared, which is 25, and 13 squared, which is 169.
Okay.
So then you subtract 25 from both sides, which leads to x squared equals 144, and then square root, you get x equals 12.
Aha. So right. So when we have x squared equals 144, we're going to solve this. We're going to square root both sides, and we get x equals 12. Now, did you guys solve equations with square roots in them in Algebra 1?
Yeah.
You did?
Yeah.
Okay. So when you take the square root of both sides like this, positive 12 is an answer, but so is negative 12, right? Plus or minus 12 here, potentially. All right, so we should say positive 12 and negative 12, okay? And so you might say, but Mr. Widmeyer, we just took square roots way back. Like here, for example, square root of 63. When we took this square root, you didn't tell me to put a plus or minus in here, or the square root of 42, which we left, or square root of 192 when we simplified it. We didn't put a plus or minus in front here. Why are we putting a plus or minus in front here? Okay? And this is something that kind of like confused me for a long time, but now I know what the difference is. When you come across a square root kind of like in the wild, right? So you're like doing some math, and you come across a square root that you have to simplify. Something like this, okay? When you take the square root of this, 63, and you simplify it, then your answer is just positive 3 root 7. However, when you come across an equation that has squares, and you're taking the square root of both sides, now you need to use the plus or minus here, because in an equation, you're looking for all the possible values of x that make the equation true. If we only say positive 12, that's not all of the possible values of x that would make this equation true. Negative 12 would also work, because when you square negative 12, it gives you the same values when you square positive 12. So that's why in an equation setting, when you square root both sides, that's where you want to put the plus or minus. Okay? Because that you want to give all the possible solutions, not just the one. All right, let's try another one here. 16 squared equals 8 squared plus x squared, like that. All right, so let's see here. So, John, how do we solve this one?
Well, first you gotta, change 16 squared.
That's okay, I'll tell you. It's 256, that's right. So we want to square the 16 and square the 8 then too, right? So yeah, 64. And then what?
Subtract the 64,
Both sides, right? Okay, so we end up with, it'd be like, what, 92, I think?
Yeah, it's 192.
192, I can't do math. Okay, there we go. It goes x squared. And then what here, John?
you square root.
Square both sides, you got it.
That can't work.
Okay, is 192 a perfect square? Well, let's take a look here. Square root 192, ugh, it is not. So we just sit here and we say x equals the square root of 192, that's our final answer. Yeah, we should try and simplify it, that's right. So you guys can do the factor tree method here, or you can, just look for, like, guess and check perfect squares, divided by perfect squares, and you can be like, all right, 192 divided by 4. Oh, well, what do you know? 192 does divide by 4. It's equal to 48. All right, so John, which do you prefer, the tree or the, you prefer to use the tree? All right, so let's just use the tree. So 192, okay, break that down to be.
You break it down to 96 and 2.
Okay, so 96 and 2. Yeah, that's always an easy one to see if you have an even number, right, and you know it's got to be divisible by 2. How about 96 then?
12 and 8.
Ah, okay. And then what?
12 can go to 4 and 3.
4 and 3.
And 8 can go to 4 and 2.
4 and 2, okay. And then the 4 is, 2 and 2. And 2 and 2. Okay. So let's see, we got a pair of 2s, got another pair of 2s, and another pair of 2s.
So then it'd be 8 and square root 3.
Very good. 8 in front, because it's 2 times 2 times 2, and then the square root of 3 left over there. It didn't do anything. So yeah, so that would be your final answer there, we want to say. And again, technically plus or minus. Technically plus or minus. All right. So all that stuff to prepare us to be able to do the Pythagorean theorem. Now you guys have used the Pythagorean theorem before, right? Ooh.
No.
Blank stares. Yes? Yes, some of us? Okay, maybe?
Wait,
Don't remember?
I don't know.
Okay, don't know?
If I probably know.
That's right.
Oh, yeah, okay, yeah.
Okay, so in a right triangle. So if I have a scalene triangle, can I, or not a scalene, if I have an acute triangle, can I use this? No. If I have an obtuse triangle, can I use this? No. Only in a right triangle. So like all the triangles we're going to be trying to deal with in this unit, okay, that's what we'll be able to use this for, in those right triangles. In a right triangle, okay, given A, B, and C as shown, and I'll just kind of draw a random right triangle here. Okay. Then A squared plus B squared equals C squared. Or if you want it more generally speaking, leg squared plus leg squared equals hypotenuse squared. Alright. So that goes back to what we saw earlier. Right? I promise I'll bring it back up. But that's what we go back to what we saw earlier, right? Here we did a leg and made a square off of it. Here we did another leg of that right triangle, made a square off of it, and then we made a square off of the hypotenuse. And the leg squared plus the leg squared, together those two combined to make the hypotenuse squared, right? Same deal for this. We took a leg, made a square, cut it out, took the other leg, made a square off of it, cut it out, and they fit perfectly inside the square here of the hypotenuse. So that was the Pythagorean theorem that we were looking at there. Okay? Or one kind of like just an example of how it works, or it at work. Okay? So what we're going to do now then is we're going to use Pythagorean theorem to find missing values. So here's some examples of how we might want to use this. Okay, so let me draw a picture here. So let's see, let's say I've got, and this picture is not drawn to scale because I can already see that I didn't do a great job there, but that's great. All right, so there's our situation. Got a triangle there, and then I got a little segment there that's being shared by the, well, it's two triangles sharing a side there, or you can think of it as one triangle too. All right. So Tanner, can we use Pythagorean theorem here to solve this?
Yeah.
All right, so how would we go about setting it up then?
You do 4 squared plus 6 squared equals c squared.
Where'd you get the 4 from? I don't see any 4s there.
Is this, they're both segments are equal,
Ah, both these pieces are equal, okay.
and it's 8 divided by 2.
There you go. So this individual piece right here is 4. Now, why couldn't we use this 8 side here to find that?
Because it's not a right triangle.
Right, so that's important here to recognize, guys, right? We have this triangle, this big triangle. It is not a right triangle, so we cannot use Pythagorean theorem here to solve for missing pieces. We need to use a right triangle. Now, here's a right triangle, or here's a right triangle right here, okay? And so we want to use the Pythagorean theorem on those. That x is one of the sides there, okay? So how would we set this up then? What would it be? So we're going to start with a squared plus b squared equals c squared. All right, can I just plug any of these numbers wherever I feel like in the a, b, and c there, Tanner?
No.
No, okay, so what has to go where?
You do 4 squared plus b squared.
Or the x squared, whatever you want to say there, yeah. I'm going to put the x in just because, I don't know, I got an x, so I'm just going to plug in the x. But if you want to leave it as b squared, that's okay too.
6 squared.
Equals 6 squared, right, okay. That hypotenuse, everyone, is super important. Make sure you are plugging in that 6. It's the hypotenuse, okay. It's opposite the right angle, okay. And there it is. So yeah, now we'll just simplify. All right, so 4 squared is 16. And let's see here, 6 squared is 36. And so we'll subtract 16 from both sides. You get x squared is 20. And what's that, Maria? It's not. So we got to take the square root here. We get x equals, and then we get to simplify that square root of 20 there. So let's see. Square root of 20. Maria, how can we break down the square root of 20? 10 and 2, okay. 5 and 2. Great. And so we have a pair of 2's, yeah? So then what does the square root of 20 simplify to be? Exactly. What's left over, the 5's left over there, so it becomes the square root of 5 there. That's right. Should we put the plus or minus here? It's an equation. We did. I can still put the plus or minus in front just from simplifying. Should I put a plus or minus in front here? What do you think?
No, you look at triangles, you can have a negative one.
Right, in the context. So here's like another kind of like layer we have to consider, right? We're talking about a triangle, and a negative length of anything doesn't really make sense, and so we're going to leave just the positive version. So again, even though we're in an equation setting, and it would normally, without the triangle there, if we were just solving this random like problem here, without the triangle, we would put a plus or minus. But because it's a triangle side, I'm going to I'll put the plus or minus, but then I'll just X out the minus side, because we don't want to worry about negative side lengths or anything like that. We don't want to have negative side lengths. Okay. All right. Let's try another one here. Any questions so far? All doing okay? All right. Let's see how much. Okay, so this has got x and y in it. All right. So this one has x and y in it. Patrick, how might we go about setting this up? Any ideas?
So you would take the square of 13,
Okay, 13 squared.
then subtract the square of 25, and that would be x.
Okay, x squared. So let me set it up using the Pythagorean theorem, but I see what you're saying. You're saying, I mean, you kind of like you jumped ahead of stuff. That's great, that's great. But just for the setup there, so yeah, there's our c squared, there's our a squared plus our b squared. I kind of flipped the order around there, but that's that. And then so, let's see, that's 169, and you're going to subtract the 25 from the 5 squared over, right?
Yep.
Okay, and so what does that leave us with? 144, doesn't it? Well, that's convenient. And so then what's x got to be here, Patrick? 12, that's right. Okay, perfect square. 12. Okay, great. So let's see, now that we have that, let's go to someone else here. Let's see. So Mason, now what?
We can put 12 squared plus 8 squared equals y squared.
There you go, exactly right. So now I can say 12 squared plus 8 squared equals y squared. Okay. Mason, could we have solved for y first here?
No,
Why not?
because you can't solve for 2 variables in the same equation.
Yeah, with one equation you can't solve for 2 different variables. You need 2 equations. So we had to solve for the x first, and then use that to solve for the y. That's right. So let's hear. So 12 squared is 144. 8 squared is 64. Ooh, 208. All right, and then what here, Mason?
You would times square root of both sides.
Yeah, all right. So we get to simplify 208. Fun. All right, so let's see here, Mason. So 208, how can that break down?
1 and 4 and 2.
Yeah, 2 and 104. Okay, what else then?
You can break down the 1 and 4 to 52 and 2.
52 and 2, okay.
And then 1 and 6 and 2.
Yep, 2 and 26.
13 and 2.
Yeah, and 2 and 13 there. So let's see. There's one pair. Whoa, there we go. 2 pairs. Okay, 2 pairs of 2, and so that leaves then y equals what?
4 times the square root of 13.
4 square root of 13. That's it. Okay. That's it. Okay. All right, let me give you guys one to try here, and then we might. Actually, I'm going to give you maybe. Ooh. All right, yeah. I'll give you 2 to try here. Okay. All right, so try these 2. I hope I don't make these too hard, but we'll see. I'll come around to help if you get stuck. I'll draw that in to help. Okay. Okay, so there's your first one. So solve for that x right there. I'll give you another one here. there's two for you guys to try. And some of you are probably thinking, those don't look like Pythagorean theorem problems at all, but they are. I assure you. Okay, so again, the idea is to solve for x. Solve for x. And I'll kind of come around and help check as necessary. And I guess I should probably put, sorry, I gotta put one more measurement in here. This side right here we're going to call y. And this is also y as well. Okay, there we go. See if you can find right triangles. Remember, this Pythagorean theorem requires right triangles. So look for those right triangles. Try and set those things up. Get stuck or something, let me know. Can you control their key? Okay. Let me try it. There you go. Thank you. Yep. Okay, let me help on that right now. Oh, wrong page. Alright. Good, and good, yeah, that's right. I'm just gonna have to do the front here, okay? So take this. Okay. Oh, you get, actually, let me get the key, and ask that, I'll be coming back, okay? What's that?
What's the pink for the second number?
225. So that creates, you have this part, you have a right triangle here, right? What's this length right here? X. Why don't you label that as X? And then you have 1, 2, 3 pieces of your right triangle. So set up the Pythagorean theorem. Yes. Yes. This length is y, this length is y. Yes. Those both y. Comes right there. That means 1 of 2 is left inside that. So yeah, that means 1 of 2 is left. That means like so like okay, here, 12 squared plus 4 squared. You're saying 12 is the leg, and x is the hypotenuse. So, yeah, so that 2 gets left out, so it stays in the square root because it's not a pair, so it stays. Yeah.
Wait.
What? What, so the 2, because there's nothing to pair up with, so it just goes and stays inside.
12 is what part of this right triangle? And then 15 is what part of this right triangle? Okay. Make sure you guys put those pieces in the right spot. Yeah, looks good. All right, we're just gonna do the front side here. All right, I'm coming around here. Oh, okay. That's why you're right. So, okay, this is good. I think you just, a little error here. So there were 1, 2, 3 pairs of 2, and we had 2 left over. So it's 8, and only 2 that didn't. Because this 2 didn't pair up with anything else. So that would still be a 2. Okay. But the 8's run. Okay. Otherwise it's here. Yeah. Good job. There's the front. Come on. All right. Great. Might be not going to. Yep. It's good. Just the front. Okay. Okay. Just the front there.
I'm coming.
Yep. Good job. Just the front there.
Looks good. Good job, Tisha. Just the front.
Yes, sir.
So I got the pairs of 2.
Mm-hmm.
So now I put.
So 3 2s go out front. 2 times 2 times 2. And then you have 1 2 that's unpaired, right? So it stays inside the square root. So square root of 2. Like that. And then you just finish multiplying out the 2s.
Is that all done? 8. Okay, look, is this 8? Where's the, oh, this is the first one here. Where's 8 with this? All right there. Okay. Be careful with this one. 12 is what part of your right triangle? Oh. All right? That's okay, yeah, that's, but again, that's what, we want to make sure we don't have that happen. Okay, good. All right, okay, that's right. So, square root of 81 should give you just, look, there's no other pair of 3s. 3 should not be, there should not be root 3 there. Both 3s are paired up. There's nothing left over, so there is no square root. It's just not. Just not. Fix it now. Okay, so that one's right. Let's check. You're saying that square root of 38 is that 2? So you're saying, hang on. It should be 128, I think. 144 is yes, that's right. There goes the front, okay. Alright, 1 second, I get it right. Okay, so you got, did you get X? Okay, but the full length, yeah. But you're right. Okay, just, okay, just front there. Yeah. Right, good job. Well done. All right, you fixed it? Well, close, not quite 8. It's close. You're missing, like, there should have been a 2 that didn't get paired up. Was there a 2 that didn't get paired up in your factor tree there?
Yes.
I'm confused on how I should sort this out.
So
So this is X and then progress.
the whole length is, well, not the whole length, that part's fine. First find the Y is what I'd recommend. Because you need to know Y before you can find X, because X is the full length and you need to know those Y's.
If I'm finding Y,
Mm-hmm.
that's 15 and 12, right?
So yeah, that's size 12. Yep. Mm-hmm. There you go. Yeah. Go from there. All right, I'm coming, guys. Hang on.
Yeah. Just the front. You think you got it now? No. Nope. Come on. Wait, where are we going? Right. So, 1, 2, 3 pairs of 2, and a 2 left over. So, 2, 2, 2 out front, and a 2 left over, so 2 goes, that's 8. 8, yeah.
That right, no.
Well, write it out. I know, take your time to get it right. That's what you gotta worry about. Got something there, Patrick? Okay, so 2 root 8s there, good. I think that would be, I think that's y that you found there.
Oh.
Because then x is the full length. So, I mean, but you're gonna get, I mean, so yeah, finish it off, but I'll go, well, you'll be fine. So just the front there. But yeah, you see, you just found the y.
Well, then X is good.
And then x is 38, yeah.
Is it all marked?
That's it.
I didn't go all of that.
Oh, did you? Okay, were you able to figure them out? Because we had to talk about it.
Yeah. This one, that's where that's over here. Oh, you know what?
Yeah. Okay. Yeah. Okay. That's actually good. We'll talk more about that tomorrow. Yeah. Good. Just for right.
No, standing up.
Yes.
I'm pretty sure I'm not. X is 12 and Y is 9.
Not quite. Here, let me go over this one real quick. So let's see here. So the x would go right there, and so then this is 4 because of 10 minus 6. Bless you. So we get x squared plus 4 squared equals 12 squared. I'm going to get to yours in just a second here. So x squared plus 16 equals 144. So x squared equals 128. And so we square root both sides, and then the 128 breaks down to 2 and 64. Ooh, 2 and 32. So 1 pair, 2 pair, 3 pair. And so that's going to be 2 times 2 times 2 times the square root of 2, because there's 1, 2 left over. So it's going to be 8 root 2 is your x there. Questions, Ishan?
Calculator. Thanks.
You're welcome.
That's
Okay.
on my phone.
Oh, okay. Wow, I never thought teenagers could do that. I thought they were attached to you, like they were part of your, they were like one of your organs or something like that. Anyway, so then this one, did you solve? So for y, okay, so like here's a right triangle right here, right, Keegan? Like right there's a right triangle, and so we want to find this side of that right triangle. What's this side of the right triangle? 12. So yeah, so how would I set that up in the Pythagorean theorem? It's gonna be a squared plus b squared equals c squared. So
It's Y squared plus 12 squared
Mhm.
plus 15 squared.
equals 15 squared, right? Okay, so good. So y squared plus 144.
Equals 225.
Uh-huh.
And minus 81.
So it's 81?
Y squared is 9. Y is 9.
So y is 9. That's right. Okay. And then,
Extra.
so that's 9. That's 9. What's this piece?
That's it. 20.
20. So to find x,
29.
20 plus 9 plus 9. Or 9 plus 20 plus 9. This part's 9, this part's 9, that part's 20. So 20 plus 9 plus 9 is 38. Is the x. See that?
Yeah.
Okay, so that's the idea.
That's not as complex as I thought it would be.
Yeah, I know that.